Well, it's time for us to do our practice with related rates, which means we really get to start delving into word problems and that fun interplay between language and mathematics. We hear these descriptors, here's a sentence describing what's going on. How do we transform that into a formula, an equation, something we can work with? Well, the answer is we practice. We learn to recognize certain things. So we're going to have a lot of practice in doing that because, well, there's going to be a lot of word problems going on when we talk about related rates. Now, it's important that you get that practice in and do as much as you can on your own. And when you're following along, if you haven't done the problems yet, make use of the pause button. Follow along, and then if you say, wait, I think I see what to do, pause the video and work it out on your own. And then you can unpause and say, yep, I did it right. Or maybe you're like, I need another idea. Don't worry, we have a couple of ideas ready for you. Well, time for us to begin. So our first problem. A 10-foot ladder is leaning against a wall, and the bottom of the ladder is currently 6 feet away from the wall and sliding away from the wall at a rate of 2 feet per minute. How quickly is the other end of the ladder moving down the wall? Now, one of the things you're going to notice is that if you read a lot of calculus textbooks about related rates, ladders are incredibly dangerous. They're sliding everywhere. So this is sort of a classic type problem. So we want to start getting into drawing our picture because we want to translate what's happening. And one of the easiest ways to do that is if there's a visual way to think about the picture, that can help. Now, as far as pictures go, you might say, well, how good do they need to be? Because you can imagine you're like, well, I'll start by drawing myself a ladder, and let's see, it's 10 feet, so maybe I'll try to put 10 rungs in there. And, well, whoops, I came up short. Well, and the question is, okay, does it help if your picture is very accurate? And the answer is no, it doesn't help if your picture is very accurate. If anything, you're sort of losing sort of the fine finesse, because you might say, well, isn't this picture good? I mean, you can label it 10 feet. You can also talk about here's how far away from the wall it is. Well, it's currently 6 feet here. And isn't that the right picture? The problem here is that we want our pictures to be very, very simple. The more ornate we make something, it's not a bad thing. And certainly there is a time and place for beautiful pictures. But we lose our simplicity of setup. So, for example, in here, it's much easier to say, let's just have, here's the floor. We don't really even need to label it, but I will because I can. Here's the wall, and here's our ladder. So there's our ladder there. All right. See, that's a very simple picture, and so it's a lot easier to think about what's happening. We say, okay, well, the ladder, it's going to slide down the wall, so it's moving down the wall. Now, we only really have a snapshot of what's happening, because we don't have the full behavior. You can imagine it might be moving slower or faster at any given moment in time. But what we're told is what's happening at a particular moment. And what do we see? Well, first off, it's a 10-foot ladder. The fact that it's a 10-foot ladder, that tells us that the length of the ladder is going to be fixed. The ladder isn't somehow growing longer or growing shorter. It's at 10 feet. So that's 10 feet. So that's a non-variable, a constant. What is changing? Well, what is changing is how far the ladder is from the wall, and of course, how far up the wall the ladder is. So since these are two things which are changing, they deserve to have variable names, so something attached to them which could represent that they change. So let's call this x and y, just because we're so used to working with the variables. Now we say, aha, wait a second. Really, when we think about the picture here, there's a triangle, and it's the right kind of triangle. So our relationship is x squared plus y squared equals 10 squared, also known as 100. So we now have our relationship. Okay, so what's next? Well, we should also identify what do we know. So in other words, in terms of x and y, what do we know? So let's scan through our statement and extract pieces of information. So it says the ladder is currently 6 feet away from the wall. So that's something about x. So we're told that x is equal to 6. And that's, again, at that particular moment, not for all time, but at that particular moment. And it's sliding away. They italicize the word away. We'll think about what that means. At a rate of 2 feet per minute. Now, what does away mean? Well, it means that if I think about my distance, x, it's getting bigger. In other words, it's moving further away from the wall. So that says that our derivative of x, which is our rate for x, is going to be equal to a positive 2. Okay, so that's our data. In fact, those are the only two numbers we have. So, okay, that's fine. What do we want? Okay, it's good to have our goal in mind. We want what? Well, how quickly is the other end of the ladder, so that's this end of the ladder, moving down the wall. So we want to understand dy dt. Okay, now, question. Is there anything else we can conclude without taking derivatives? Well, I claim there is. You see, there's a relationship between x and y, and we've been told what x is. So we can use that relationship to figure out what y needs to be. So if we plug x into our relationship, we get the following, namely that 6 squared plus y squared equals 100. Well, 6 squared is 36. Move 36 across. We get y squared would be 64. Take the square root, we get 8. Now, you might say, wait a second, shouldn't it be plus minus 8? Well, no, ladders don't go into the ground. So we can use context to figure out what's true. So we know x equals 6, and we know y equals 8. So we can add that to our list of things we know. In fact, we know both of our variables, and we know one of the rates. The only thing we don't know is the missing rate. So that's why we'd like to get a relationship between the rates. Aha! We have a way. These rates are related. Mwahaha. Okay, so our next step. We're going to start with our x squared plus y squared equal 100. And remember, we're going to think of x and y as both being functions of t. See, we're looking for how do things change with time, t. So, taking the derivative of x squared will be 2 times x to the 1 times the derivative of x with respect to t, which is dx dt. Then we go to the derivative of y squared. The 2 comes down, y to the 1 times the derivative of y with respect to t, dy dt. And, of course, that's going to equal the derivative of 100, which is 0. All right. Great. Good. Good. Well, now the last step here is to say, hey, we have a lot of these pieces of information. So let's plug in what we know. So we have that 2 times 6 times 2, because dx dt is 2, plus 2 times 8 times dy dt is equal to 0. Well, all right. Well, 2 times 6 times 2 is 24. And then I can move the 24 across, so we get 16 dy dt is equal to negative 24. And which says dy dt is going to be equal to negative 24 over 16. And, well, they both are divisible by 8. So that's negative 3 over 2. So, what's our answer? Well, we know what dy dt is. It's negative 3 over 2. But we can now answer the question. We can phrase it. We can either say it's negative 3 over 2, or we can be a little bit more careful. So, for instance, what if I wanted to talk about units? Well, our distances were measured in feet. It's a 10-foot ladder. We're 6 feet away. We're 2 feet per minute. What was t measured in? Can you see what the answer to that? T was measured in minutes. It's given right here. See, dx dt. The units of dx dt are the units of x over the units of t. Since x is measured in feet, t must be measured in minutes. All right, so we could say -3/2 feet per minute. And if we were going to be talking in a normal conversation, which, sometimes mathematicians have been known to slip up and engage people in normal conversations. It happens on occasion. We could answer it in the following way. We could say it's sliding down the wall. And how do we know it's going down? Because it's negative. So the y value is decreasing. It's getting a shorter length. Sliding down at 3/2 feet per minute. That's how we could respond if we wanted to use more of our language abilities. Okay, good. Well, that was a nice warm-up. We're not going to go into so much detail on every problem, but we want to make sure the first couple we get down pretty well. All right. So let's kick it up a notch. So, you are a lighting technician helping to set up the lights on a large stage for the Paddy Carey rock concert. Now, a bright light is currently turned on, is 10 feet above the ground, and slowly being hoisted up at a rate of 2 feet per minute. A microphone stand, which is 5 feet tall, is set up nearby and is currently casting a 12-foot shadow from the light being moved. Determine the rate at which the length of the shadow of the microphone stand is changing. So it's helpful to think about the picture. So what do we have? We have a light source. So here's our spotlight, and it's being hoisted up, and it moved up, right? So that's what hoisted. So it's being moved up. So there's this chain here, and they're moving it up. Now this light, of course, it's shining. And what do we see? Well, we see nearby there's a microphone stand. So here's our microphone stand. And what are we told? Well, that it's casting a shadow. So we have to think about the shadow. So there's this light coming down. So there's this shadow here. So here's the shadow. All right, so there's our rough drawing of our situation. Now, we want to start thinking about trying to label things, identify what's important, what's not important, and so forth and so on. All right, so let's think about it. One of the things is anything which has a number very likely is going to play a role in giving us our answer. So we see here's a number, 10 feet. So if we think about what that means, if we draw our triangle here, that says, lo and behold, this is 10 feet, the height of the light. All right, and it's slowly being moved up, and it's moving up at a rate of 2 feet per minute, which means this is something which is varying. So, all right, we should give this a variable name. We'll call it y for now. Y usually is a good variable name for things in a vertical direction because we're used to that. So let me just make a side note here. We're told that y is 10 and dy dt is equal to 2, and it's a positive 2. Keep attention. You want to make sure you have the right sign, because you might say it's changing at 2 feet per minute, but is it changing in a positive or a negative way? In other words, is the length shortening? That's negative. Is the length increasing? That's positive. Now, a microphone stand, we know that it's 5 feet tall and it's set up nearby. Now, the microphone stand isn't changing length. It's just an inanimate object. Nothing's happening to it. So we don't need to give it a variable name. So we're going to call it just 5. And it's currently casting a 12-foot shadow from the light being moved. Now, the thing is that as the light moves, the shadow moves. So the shadow is going to be changing as well. So we shouldn't just write down the fact that it's 12. We should give it a name. So let's call it x. So what do we have? We have that x is 12 because it's a 12-foot shadow. So when I talk about x, specifically x is the length of the shadow. All right, so there's what x is. Now, the question is, how is the rate at which the length of the shadow of the microphone stand changing? Well, dx dt is, and whatever that is, there's our answer. In fact, we even can write down our units if we needed to. Our answers will be in feet per minute because all our distances are measured in feet and our parameter time t is measured in minutes. Okay, so let's see. We should have highlighted, we have 10, here's 10, there's 2, there's 5, there's 12. See, there's all the numbers. We're grabbing the data. All right, well, what can we do? So let's redraw our picture a little bit more simply now. So what do we have here? We have the following setup. So this is 5. This length here is x. And this length here is y. Now, what do you see in this picture? What's the right kind of object we have? Well, this picture has similar triangles. You see there's a large triangle, which is from the light source to the end of the shadow. All right, and then there's a small triangle, which is the microphone stand, to the end of the shadow. Similar triangles means that there's a relationship between them. So we need to know one more piece of information, namely, how far is it from where the light is to where the stand is? Well, we can figure that out. How can we figure that out? Well, we can say, look, let's write down this relationship. So the relationship from similar triangle says that the ratio, so for example, x is to 5 as this longer side, so x plus some unknown distance, is to y. Now, the good thing is, at our particular moment in time, we actually have enough to figure it out because we do know some time where there's relationships explicitly between x and y. So I can plug in what we know. We can say 12 is to 5, because x is 12, as 12 plus something is to 10. Now, multiply both sides by 10, and you'll see that you'll have 10 divided by 5 is 2, so you get 24 is 12 plus something. Or you can say, aha, this unknown distance to the microphone, we know what this is. We can now say this is 12. So here we go, that's 12. All right, now we have our relationship between x and y. And you say, well, perfect. Well, if we have our relationship between x and y, why don't we just take a derivative? Well, yes, we could, but let's be nice to ourselves, because I think it's important to treat ourselves nicely. So what does it mean, be nice to ourselves? Well, here I see that there's a quotient going on. I don't like quotients, and I prefer not to work with them if I don't have to. And here's a case where we don't have to. So what we can do is we can cross multiply. So if we cross multiply, what do we get? We get that x times y is equal to 5x plus 60. Right? Because we're going to multiply both sides by y, so that gets rid of the y here, multiplies by y here, and both sides by 5. And of course, when you multiply by 5 over here, make sure you distribute through. So, we're almost there. I can almost fit it downstairs. I'm going to move up a little bit. So, take the derivative with respect to t on both sides. And what do we have? Well, x, y, product rule. So we're going to get derivative of the first, dx dt, times the second, plus the first, times the derivative of the second, is equal to 5 times the derivative of x, which is dx dt, and then, of course, the 60 goes away. Now, let us plug in what we know. What do we know? Well, we know y, dy dt, and x. So, this becomes dx dt times 10. So 10 dx dt plus 12 times dy dt. So that's x is 12, dy dt is 2, so plus 24 is equal to, then it's 5 times dx dt. Now we can move the dx dt across, and we can say, hey, negative 5 dx dt is equal to 24, and now we're almost there. Divide both sides by 5, and what do we get? Well, we get that dx dt is negative 24 fifths feet per minute. Okay, and there's our answer. That's the rate at which the length of the shadow is changing, 24 fifths feet per minute. And notice the negative. That means it's getting shorter. Let's think if that makes sense. If you were to move the light up, so the light were shining up from here, and you were to cast a shadow, it does get shorter. So we should expect it to, yes, the shadow should be getting shorter. So that's good. It matches with our understanding of the problem. So this is a case where we have similar triangles. We will have more triangles in our practice as we go through and do them all. So it's good to get the hang of them. All right. Well, let's do another problem. Okay. You are 10 kilometers away from a rocket launch. Close enough to hear it, but not so close as to be instantly vaporized. I think that's a really good sweet spot. You know, it's nice to not be instantly vaporized. You are filming the rocket as it goes up. Now, given that the moment your camera forms an angle of pi thirds radians with the ground, that the angle is increasing at a rate of 0.2 radians per minute, find the speed of the rocket. Ah, okay, good. Well, let's draw a picture. So we start drawing a picture. We'll draw a little bit stylized diagram perhaps. So here's our ground, and then of course we have our rocket going up. And, well, I'm probably overly embellishing here. This is probably, I had fun when I was an undergraduate. I got to take a nice drawing class. And I remember the instructor. He was a wonderful guy. He was from Africa, and he came in the first day of class, and he said in this beautiful accent, "I do not believe you cannot become good artiste, but I do believe you cannot become good draftsman." And I like that idea. It's like, look, maybe we're not going to become perfect artists, but we have the ability to become competent in our basic skill sets. It's kind of like math. Look, I don't believe you're going to all become maybe mathematicians, but I do believe you can be able to develop the basic tools and abilities to understand mathematics. So, okay, so we have our rocket going up, and here's us. We're very small. That's probably actually too large even for the scale. And so we're viewing the rocket. So here we go. Now you'll notice right away, we're forming like a nice right triangle. This assumes, of course, the rocket goes straight up. If you ever watch rocket launches, it does tend to veer, but for right now we'll say it's in still the straight up portion. All right, and what do we have? Well, we know a couple of things. As we read along, we see numbers. We see the number 10. So that's this distance here, and this is not changing. So that's staying put. That's what it is. So we're 10 kilometers away. All right, and what else? Well, we have this distance here, which is the distance the rocket is. Well, that's changing, and we're not told how high the rocket is, so we don't know it. And, well, we'll live with that for right now. We do know that there's an angle. Okay, so that means that we need to put our angle into the picture. So let's put an angle in, and we'll give it an angle name. Theta is a very popular angle name. So there's our angle, and now we have our nice diagram. Okay, and what do we know? Well, we're told that our angle is currently pi thirds. So we're told theta is pi over 3, and the angle is increasing at a rate of 0.2 radians per minute. So that's talking about when you see words like increasing, decreasing, that means there's a rate involved. So that means that the change in theta with respect to time is 0.2 radians per minute. Okay, so that's what we know. So we don't know why, and what do we want? Well, what we want is we want to find the speed of the rocket. Now, the good news is we're actually going to know our answer, because really when we're asked to find the speed of the rocket, we're really after dy dt. Well, we know how our units are being measured. They're being measured in kilometers. We also know how time is being measured. They're being measured in minutes, so kilometers per minute. See, the nice thing is that math just has a way of getting the units right. We can just figure it out by looking at things. We don't have to keep track of the units as we work the problems, because the units at the end will always be the right units that we need. So, now we think. Now, is this a Pythagorean theorem problem? And the answer is no. Well, what's sort of the clue? The clue is this angle theta. See, the Pythagorean theorem doesn't care about the angle. So we say, okay, but it still is a right triangle, so there's probably something involved. Well, let's think about what we have. We have an angle, and then we have the opposite side to that angle, and the adjacent side to that angle are the distances that we know information about or that we want to get information about. So, what connects the opposite and adjacent sides to a particular angle? Well, tangent. So, what we can say is that the tangent of our angle theta is equal to our opposite side over our adjacent side. Or we could say that y is 10 times tangent theta. Good. Progress. Progress. Now, what comes next? Well, we have our relationship, so we're going to take the derivative with respect to time. So we can say, dy dt is here chain rule. So tan is a constant, derivative of tangent is secant squared. And then times the derivative of the inside, which is derivative of theta, d theta dt. So we're almost done. What do we need to do? Well, we need to know what our pieces are. We know what theta is, so we can plug in pi thirds into there. And we know what d theta dt is. So we could say, what? dy dt is equal to 10 times secant squared of pi over 3 times d theta dt, which is 0.2. Okay, well, let's think about this. Do we know what secant of pi over 3 is? I think we probably can figure it out. Now, secant is one of those things which most people are not comfortable with off the top of their head, but if you remember, secant is 1 over cosine. That can help. So this is 1 over cosine of pi over 3. Now, do you know what cosine of pi over 3 is? That's also, by the way, cosine of 60 degrees. So if you think about the unit circle, and you say, well, where is pi over 3? It's roughly over here. So the question is, what's the x value? And the answer, cosine of pi thirds, is a half. So 1 over a half gives 2. So this part right here would be 2 squared. So what do we have? We have 10 times 2 times 2 times 0.2. Well, notice that 10 times 0.2 is another 2, so we put all that together and we get 8. And therefore, we see, lo and behold, this is moving at a speed of 8 kilometers per minute. All right, and there you go. That's the speed of the rocket. So by measuring, the rate at which that angle is changing, we can keep track of how fast the rocket is moving. So this is why there's this nice relationship. It's like, well, I want to measure something that's far away from me and how it's changing, but I can do it by saying, well, what's something close to me and how is that changing? And let me figure out the relationship between them. There's a lot of power in related rates. It's good that we're learning about these things. All right, on to the next problem. Okay. Now, from an island, you head east on a boat. A short time later, your friend heads north on another boat. Well, that's pretty good. We probably couldn't have the same boat at the same time. Later, your friend calls on the radio and asks how far you have gone. I don't know, but right now my speed is 1 mile per hour. Your friend replies, I have gone a few miles, and right now I'm only doing 1/3 of a mile per hour. I guess your friend is a little bit older, but that's all right. The radio indicates that you are currently 5 miles apart and moving apart from each other at a speed of 1 mile per hour. So, the problem, find the distances you both have traveled. Well, this is interesting. Now, why is it interesting? Well, notice what we're looking for. It's telling us we're going to find not one thing, but two things. We're going to find distances. In particular, though, that means we're not looking for rates. Our answer is not a rate, which makes you say, what? How is this related to rates? Well, let's draw a picture. So I think we can be very simple here. So here's our island. Then we are heading which direction? We are heading east. So that means we're going this way. So here is us. And then here is our friend. Okay, so let's label X is how far we have gone, and Y is how far the friend has gone. And then, of course, there's the distance in between. And that we'll call Z. All these three things are changing. X is changing, Y is changing, Z is changing. So everything is changing. But of course, if I draw the picture well, you'll see, look, it's a right triangle. Because if you think about it, you have what? You have the direction east and you have the direction north. And if you put those together, you get a nice right triangle. Okay, well, now we say, aha, there's our relationship. This is the Pythagorean theorem. So our relationship is x squared plus y squared equals z squared. Just as we would expect for the Pythagorean theorem. Very Pythagorean theorem-like. All right, what else do we know? Well, let's read through it again and see what we can spot. So your friend calls, don't know how far. Let's see. This is us. I don't know, but right now speed is 1 mile per hour. So that's how fast we're moving. So that's for x. So dx dt is equal to 1. Your friend replies, okay, that's the y. I've gone a few miles, and right now I'm only doing 1/3 of a mile per hour. All right, well, they're enjoying their time out, maybe practicing a little bit of social distancing or something. All right, so they're going 1/3. And the radio says, hey, we know how far apart you are. So we're told z is equal to 5, and we know that we're moving apart from each other at a speed of 1 mile per hour. So dz dt is equal to 1. All right, there we go. We got it all in. Okay, so we know all the rates. In fact, every single rate is given to us. So it's not about finding the rates. So where does related rates come into play? Well, remember, related rate says, hey, there's a relationship going on for your rates. So that can be a useful relationship to give us information about our situation. So let's take our derivatives. So we take our derivative of our relationship, 2x dx dt plus 2y dy dt is equal to 2z dz dt. Now, the 2's all cancel. That's nice. And now we have this wonderful relationship we can start plugging stuff into. What do we know? Well, we know all of these pieces of information. What we don't know is x and y. But we can plug it in. So what do we have? Well, we have that x times dx dt, which would be x, y times dy dt, which is 1/3 y, would be equal to z times dz dt, which is equal to 5. So x plus 1/3 of y has to equal 5. Now, that's the relationship between x and y. We also have one other relationship between x and y, namely x squared plus y squared is equal to z squared, which is 25. So, there's two relationships and two unknowns. That's the good number of relationships and unknowns to have. Now, here they're not both linear. So we got to do a little bit more of interesting things. So we'll go and do the classic, let's substitute. So what we can do is we can solve for one of the variables. It actually doesn't matter which variable you solve for. I'm going to solve for x just because that seems the easiest to do, because I just have to subtract 1/3 y. Now I can use this, plug it into there. So this becomes 5 minus 1/3 y squared plus y squared equals 25. Well, square it. You'll get 25. Then you cross multiply, you'll get minus 5/3 y, and then another minus 5/3 y, so minus 10/3 y, and then plus a 1/9 y squared plus a y squared equals 25. All right, well, what can you do here? Well, I think you can do a couple things. First off, the 25s cancel. Woohoo! Nice. All right, what else can you do? Well, hey, look, you have a 1/9 y squared and a y squared. This would become a 10/9 y squared. And then you have a minus 10/3 y. Okay, and then we can say, well, let's just pull out. And in particular, let's pull out enough so we can pull out a 10. So we have 10. And let's pull out a 9 so we get rid of our fractions. And they both have y. So 10/9 times y, then what's left? Well, you'll get a y from that term. And from this term, you grab the y, you grab the 10. Because you pulled out 9, there's only 3 there, you have to have 3 left. So y minus 3 equals 0. So, what does that get us to? Well, it gets us to two possibilities. So we now have the case that y equals 0 or that y equals 3. Now, can we eliminate one of these possibilities and why? Is there anything in the problem that lets us say one of these is not possible? Let's see what your friend says. Your friend replies, I have gone a few miles. What does that mean? Well, it means that they've gone some distance. What would y equals 0 indicate? Well, y equals 0 would indicate they haven't gone anywhere. They have yet to leave. So, we can eliminate that possibility. And therefore, we now know the answer for how far your friend has gone. So, how far has your friend gone? The answer is 3. 3 what? 3 miles. So, our friend is going to be 3 miles, which means us will be what? Well, that's our x. We plug in y equals 3. A third times 3 is 1. 5 minus 1 is 4. So we have gone 4 miles. And there we go. So this is kind of a nice, because it's using related rates in kind of an unexpected way. Oftentimes we think related rates are you have to extract a rate. But really related rates are, hey, here's another relationship which involves rates. And so if we have all the rates, that can give us information about how variables are connected to each other. That was fun. I like that one. I like many problems, though. I'm easily persuaded to like things. Okay. Another problem. A large helium balloon is tethered to the ground by a lightweight cable that is 50 feet long. Suddenly, a strong gust of wind blows, and it's causing the balloon to move. Well, wind often does that to balloons. Given that the location of the balloon is directly overhead from a point 30 feet away from which it is tethered, and that the distance from where it is being tethered is increasing at a rate of 2 feet per minute, then determine the rate at which the distance from the balloon to the ground is changing. So let's think about our picture. So we have the ground. Then we have the balloon. And so initially, the balloon was just straight up because, the balloon would pull it straight up. So here's our balloon. Now, our wind starts blowing. And what happens? Well, what happens is that as the wind blows, it's going to cause things to move. So our balloon is going to start heading this way. And so we have, lo and behold, it's going to start moving over. And so what do we get? Well, it's going to end up doing this. So this is what's happened. The balloon has all right. Well, we can now identify a couple things. So let's mark our important numbers. Our cable here is 50 feet long. And of course, this is still 50 feet long. It doesn't change the length of the cable. It's just, it's now being moved over. So, all right. And what do we care about? Well, we care about the point directly beneath the balloon. So let's mark that. So we're going to draw straight down to that point. And so we have that there's this distance x, which is how far from where the balloon is tethered to where the balloon is just above. And of course, there's a distance y, which is how high up is the balloon. Now, the question is, well, what's the relationship between x and y? Now, we can actually figure this out. In fact, the picture is very telling because we see what? It's x squared plus y squared equals 50 squared. And another way to see that is we can think of what? Well, we can see this because we have, as this balloon moves, what is it going to move along? It's going to move along a circle because it's always going to be 50 feet away from where it's tethered. So it's a circle. We're thinking of it as this point is xy, so x squared plus y squared equals r squared. Good. All right. Well, so there's our relationship. That was pretty good. Now, so let's make sure we have all our numbers right. The location of the balloon is directly overhead from a point 30 feet away. So this 30 feet is about x. So we know that x equals 30. The distance from where it is being tethered is increasing at a rate of 2 feet per minute. So dx dt is 2. And it's increasing, which means it's positive 2, which is good for us to know. And now the problem is what? Well, we want to find dy dt. The rate at which the distance from the balloon to the ground is changing. That's how far this distance is changing. So we want to be after that. Now we can, of course, even identify what the units are. So notice our distances are all feet. This per minute means that our t, our parameter, is time. So it's something feet per minute. All right. Well, how do we finish up? Well, let's just plug in what we know and also see what we don't know. Well, we can solve for y at this moment, right? Because we can plug in for x. So we get x squared, which would be 30 squared, plus y squared equals 50 squared. Well, if you square that out, that's 900 plus y squared equals 2500. Or you could say y squared is 1600, right? Because 25 minus 9 is 16. Or y equals the square root of 1600, which is 40. It's actually a lot easier to take the square root of 1600 than it sounds. Because you say, well, think about 16 times 100. Square root of 16 is 4. Square root of 100 is 10. So we also know what y is. Then finally we say, hey, I'm after a rate. Let's find the relationship. So taking the derivatives, 2x dx dt plus 2y dy dt is equal to root of 50 squared, 0. Okay, so there's our relationship. Sorry, I was writing stuff down wrong. We can divide out by the 2's. So we have, I'll write down again, x dx dt plus y dy dt is equal to 0. And now we say what? Well, x is 30. So 30 times dx dt, positive 2, plus y, 40, times dy dt, which, well, we don't know. That's what we're trying to find out. Has to equal 0. Well, good. Now, we move stuff around. There's a 60, and then we can divide, move that across, and then divide by 40. So we get, I think I can squeeze it in here, dy dt is negative 60 over 40. Well, I can definitely cancel off the zeros, which means divide by 10 on top and bottom. So negative 6 over 4, which would be what? Well, negative 3 over 2, because they're both even. I can factor out a 2. So our answer is negative 3 halves feet per minute. Now, think about the sign. Does it make sense? This says it's negative. So if our distance here is getting further away, intuitively, I'm moving further down along this circle. Should I be moving closer to the ground? And the answer is yes. So good. Our sign is correct. You see, once you get an answer, one of the things that's often useful to do is ask the question, is my answer reasonable? If it's not, you should go back and check to see what you've done, because something happened along the way. All right, let's do one last problem for this session. All right. So, a particle is moving along the implicit curve. X cubed plus y cubed equals 9xy. And given that when the particle is at the point 2, 4, that dx dt is negative 2, find dy dt. Well, this sounds initially like, they didn't give us a lot to go on. But remember, what's the first step? The first step is to find a relationship. Now, for this problem, how do we find the relationship? Well, the answer is it's given to us. We don't have to find it. They tell us to it. They've handed it to us on a nice, almost, you could say, on a silver platter. Let us not regret that. Let us not complain about being given all this beautiful relationship. So we get to skip step 1 completely. So we have x cubed plus y cubed equals 9xy. Now what else do we know? Well, we're told there's this point. It's at 2, 4, which means that x equals 2, y equals 4. You could, by the way, check. Is it the fact that 2 cubed plus 4 cubed is 9 times 2 times 4? Well, 2 cubed is 8. 4 cubed is 64. Put those together is 72. 9 times 2 times 4 is also 72. And then we're also told dx dt is negative 2. All right, so there's all our information. And we say, all right, perfect. Take our derivative. So 3x squared dx dt plus 3y squared dy dt equals, here we're going to do a product rule. See, these were chain rules. Here's a product rule. 9 dx dt times y, derivative of the first, times the second, plus 9x, which is the first, times the derivative of the second. We're almost there. What do? Plug in what we know. So, here we go. X is 2. 3 times 2 squared, 12. Dx dt, negative 2. Plus, y is 4. 3 times 4 squared, 48. Dy dt, we don't know. That's what we're looking for. Is equal to, here, we get 9 times dx dt, which is negative 2, times y, which is 4. So 9 times negative 2 times 4. That's negative 72. If you multiply it all together. Plus 9 times 2, which is 18, times dy dt. So let's see, what can we do? Well, we can move this across, and we can move that across. And if we do it, well, 48 will subtract 18. So we get 30 dy dt is equal to, so this was negative 72. We're going to bring this across. It'll be plus 24 when we bring it across. So negative 72 plus 24 will leave us with negative 48. Finally, we divide, so we can say dy dt is negative 48 over 30. Well, they both have 6, so that would be negative 8/5. All right, now, negative 8/5, what? What are our units? The answer is, we don't know. We don't know what x is, we don't know what y is, we don't even know what t is. So, we just leave it as negative 8/5. That's all right. I should comment, not every problem requires you to put units in. So, we've been doing it just out of, good habit, good practice. And, all right, well, that's a sampling of some of the things you might see with related rates, but truly just a sampling. So we're going to have a lot more practice. So if you need more practice, we're going to have it for you. So keep practicing, keep doing, learn how to translate from language into math. It's a really powerful tool, and it helps you see how the world around you is really very mathematical in nature. All right, thanks for joining me.